Welcome to this lecture for Chapter 9 of the textbook Introductory Chemistry. The title for this lecture is Chemical Quantities. In this lecture, you will learn how to read and interpret the quantitative information provided in a balanced chemical equation. We will look at the concept of limiting reactants and also reactants in excess. We'll do a number of problems involving limiting reactants and talk about percentage yield as being an indicator of the efficiency of a particular reaction. So a balanced chemical equation tells us about the relative numbers or moles of reactant and product molecules that participate in the reaction. The coefficients, or the numbers in front of the formulas for each component of the reaction in a balanced equation, they give the relative numbers of molecules. Let's look at a specific example. This equation here is telling us that ethanol reacts with oxygen to give carbon dioxide and water. It tells us more than that though. Firstly, we can see that the equation is balanced. It tells us that 1 molecule of ethanol reacts with 3 molecules of oxygen to produce 2 molecules of carbon dioxide and 3 molecules of water. It also tells us that 1 mole of ethanol reacts with 3 moles of oxygen to produce 2 moles of carbon dioxide and 3 moles of water. Now we'll look at another specific example. Here we have solid copper 1 sulfide reacting with solid copper 1 oxide to produce solid copper metal and sulfur dioxide gas under the right reaction conditions. Firstly, the reaction isn't balanced. So we need to balance the equation first. After balancing the reaction, we need to determine how many dozen copper atoms could be produced from a dozen molecules of the copper sulfide and 2 dozen of the oxide of copper 1 oxide. Also, how many moles of copper could be produced from 1 mole of the sulfide and 2 moles of the oxide. So, first thing is to balance the equation. When you balance the equation, you should have a coefficient of 1 in front of the copper 1 sulfide, a coefficient of 2 in front of the copper 2 oxide, a coefficient of 6 in front of the copper metal, and 1 in front of sulfur dioxide. Now that you have those coefficients in place, you can have a look at how many dozen copper atoms could be produced from a dozen molecules of sulfide and 2 dozen of copper 1 oxide. The answer is 6 dozen, and likewise 6 moles of copper can be produced. Okay, so now let's have a look at the mole-to-mole ratio with another specific example. In this case, we've got liquid water going to hydrogen gas and oxygen gas. So the equation's already balanced, and we can predict the number of moles of product that a given number of moles of reactants will yield. And we'll have a look at how we go about doing that. So what we can see from the equation is that 2 moles of water yields 2 moles of hydrogen gas and 1 mole of oxygen gas. Likewise, if we started with 4 moles of water, that would yield 4 moles of hydrogen gas and 2 moles of oxygen. So what's important here is the ratio in which the reactants and products interact. Have a look at the picture here. So pictorially you can see two water molecules on the left-hand side reacting to give two molecules of hydrogen gas, here and here, and one molecule of oxygen. Similarly, if we start with 4 moles of hydrogen, of water, we produce 4 moles of hydrogen gas and 2 moles of oxygen. So the mole ratio allows us to convert from moles of one substance in a balanced equation to moles of a second substance in the equation, generally a product. Consider this example where we have Na2SiF6 solid plus 4 lots of solid sodium producing solid silicon and sodium fluoride. Question is, how many moles of sodium fluoride will be produced if 3.5 moles of sodium is reacted with excess Na2SiF6? Okay, so first of all, what does excess mean? It means that there's more than enough of that particular reactant according to the coefficients of the equations. The coefficients tell us that we need 1 mole of Na2SiF6 to react with 4 moles of sodium. So the question says we have more than enough Na2SiF6. So how many moles of NaF will be produced if 3.5 moles of sodium is started with? We need to consider the molar ratio. 4 moles of sodium produces 6 moles of sodium fluoride. We need to write down an equivalent statement. 6 moles of sodium fluoride comes from 4 moles of sodium. We can write this as 6 moles of sodium fluoride per 4 moles of sodium. So where are we going with this problem? We want to determine the number of moles of sodium fluoride produced by sodium. What information do we know? Well, we know that we've got the balanced equation, and that will tell us the molar ratios in which the two species are related. We know we start with 3.5 moles of sodium. So what do we do next then? Have a starting amount. We can multiply by the conversion factor, which is 6 moles of sodium fluoride per 4 moles of sodium. That's called the mole ratio. We cancel the units on the numerator with the units on the denominator, and we're left with units of moles of sodium fluoride. So what this tells us is that 3.5 moles of sodium will produce 5.25 moles of sodium fluoride, and we work that out by looking at the numbers or the coefficients in front of the reactant and the product respectively. Propane has the formula C3H8. It's a common fuel used in heating our homes, and we can predict how many moles of carbon dioxide are formed if we start with a set amount of moles of propane. In this case, we're starting with 3.74 moles of propane. That's burned in excess oxygen, according to the equation here. Propane, 1 mole, reacts with 5 moles of oxygen to produce 3 moles of carbon dioxide and 4 moles of water. So we've got to work out how many moles of carbon dioxide are formed. The key term here is burned in excess oxygen, which means that we have more than enough of it. So the amount of products that we form is determined by the other reactant, which is propane. We start off with 3.74 moles of propane, and we want to know how many moles of carbon dioxide that can produce. You can see they're in a 1:3 ratio. So if we start with 3.74 moles of propane, we'll end up with 3 times 3.74 moles of carbon dioxide. So there are steps for calculating the masses of reactants and products in chemical reactions. First of all, we balance the equation for the reaction. Secondly, we convert the masses of reactants or products to moles. Then we can look at the molar ratio given by the coefficients in front of each species in the chemical equation. Determine the mole ratio by looking at the reactant and the product of interest. Use the mole ratio to calculate the number of moles of the desired reactant or product. Finally, convert from moles back to masses. So I'm going to introduce a new term here. It's called stoichiometry. And it's a process of using a balanced chemical equation to determine the relative masses of reactants and products involved in a reaction. In other words, if we start with a set mass of a particular reactant, we can determine the amount of product that will be formed by looking at the coefficients in front of the species in the balanced chemical equation. This process is stoichiometry. Let's look at another specific example. In this case, we're looking at solid chromium metal reacting with oxygen gas to give chromium oxide. Now, if you have a look at the subscripts in the formula for chromium oxide and note that chromium is a transition metal, then what you will see is that we actually have chromium 3 oxide as shown below. So how many grams of chromium 3 oxide can be produced if we start with 15 grams of solid chromium and excess oxygen gas? So again, the key term here is that we have excess of the oxygen gas. There's more than enough of it. So the reactant which determines the amount of product we can form is chromium. Step 1 was to balance the chemical equation. Okay, so there is the balanced chemical equation, and this tells us that 4 moles of solid chromium metal will react with 3 moles of oxygen gas to produce 2 moles of chromium 3 oxide. Now we need to know the molar mass of chromium 3 oxide, and that's a simple matter of adding up the atomic masses of the respective component elements. If we do that, we get 152.00 grams per mole of chromium 3 oxide. We need to convert the mass of chromium to moles of chromium. That's a simple matter of putting the mass of chromium over the molar mass of chromium, 0.288 moles. Now we need to determine the number of moles of chromium 3 oxide produced by using the mole ratio from the balanced equation. What you can see is that 4 moles of chromium produce 2 moles of chromium 3 oxide. The conversion ratio is 2 moles of chromium 3 oxide per 4 moles of chromium. Multiply 0.288 moles of chromium by the conversion ratio and you get 0.144 moles of chromium 3 oxide. Now we can need to convert the moles of chromium 3 oxide back to grams. That's a simple matter of using the equation by rearranging. The number of moles is equal to the mass over the molar mass. So the mass is equal to the number of moles times the molar mass. We get 21.9 grams of chromium 3 oxide. Notice that the units of moles of chromium 3 oxide on the numerator and the denominator cancel, leaving us with units of grams. And there's the steps all in one sequence. Notice the units that cancel and what we're left with. Tin 2 fluoride, stannous fluoride, is added to some dental products to prevent cavities. Tin 2 fluoride is made according to the following equation, where we see that solid tin metal reacts with hydrofluoric acid to give tin 2 fluoride and hydrogen gas. How many grams of tin 2 fluoride can be made from 55 grams of hydrogen fluoride if there is plenty of tin available to react? Now, this is another way of saying we have excess tin. Plenty of tin available to react means we have an excess of it. This tells us then that the hydrogen fluoride is actually the species, the reactant species, which determines the amount of products that we form. So if we have 55 grams of hydrogen fluoride to begin with, we need to know how many moles that is. We then look at the molar ratio between hydrogen fluoride and tin 2 fluoride, 2 to 1. We use that ratio to convert the number of moles of hydrogen fluoride to the number of moles of tin 2 fluoride. Once we know the number of moles of tin 2 fluoride, we can convert it to grams. The answer is 215 grams. And here's the calculation string. Now we'll consider this equation where phosphorus trichloride reacts with water to give phosphorus acid, and hydrochloric acid. What mass of water is needed to completely react with 20 grams of PCl3 or phosphorus trichloride? Now when we say completely react, that means that they're going to react in the stoichiometric ratios. In other words, 1 mole of PCl3 will react with 3 moles of water. And if they react in the stoichiometric ratios, then we should get the same ratio of products. So, if we start with 20 grams of PCl3, you can determine the number of moles of PCl3 we're starting with. We're going to determine the amount of water that we'll need to react with that. Since the two reactants are in a 1 to 3 ratio, we'll need 3 times as many moles of water to react with the PCl3. Then you will need to convert it to a mass, and there's the calculation string below. Let's take a look at this more complicated example here, where we have an unknown element X. Now this unknown element X reacts with boron oxide to give a compound with boron and the element X, and the element X, a compound of the element X with oxygen. They react in a 6 to 2, 1 to 3. If 175 grams of the element X reacts with diboron trioxide to produce 2.43 moles of B4X3, we need to find out the identity of X. Now this is a rather involved calculation. First of all, we start with the fact that we have 2.43 moles of B4X3. So we can work backwards in this case to find out how many moles of X formed the B4X3. Once we know the number of moles and we know the number of grams, we can work out the mass, the molar mass. Once you have the molar mass of X, you'll be able to identify which element it is by looking at the periodic table. So a stoichiometric mixture contains the relative amounts of reactants that matches the numbers in the balance equation. So in other words, of the reactants, you've got the numbers of moles as they're given by the coefficients in the balanced chemical equation. If we look at nitrogen gas reacting with hydrogen gas to give ammonia, let's take a look at this example. Okay, so the hydrogen molecule is represented as the light blue diatomic, and the nitrogen molecule is the darker blue diatomic. Ammonia is shown with the dark blue and then the 3 light blue hydrogens attached. Now, according to the stoichiometry of this reaction, 1 mole or 1 molecule of nitrogen gas will react with 3 molecules of hydrogen gas. What we've done here is circled the groups of reactants which will react. 1 molecule of nitrogen and 3 molecules of hydrogen gas. 1 molecule of nitrogen and 3 molecules of hydrogen gas. Now within these circles you can see the products. Those groupings of reactants will produce this many molecules of the product ammonia. There's no reactants left over. The reaction is a stoichiometric mixture. So let's look at this reaction again, but let's look at it where the reactants don't react in stoichiometric ratios. They're not a stoichiometric mixture. One of the reactants is going to be in excess. Now on the left-hand side here you can see that we have more than enough nitrogen. It's in excess. So we group the collections of reactants according to the balanced chemical equation, and then we form the products. Note that after the reaction is complete, the nitrogen molecules are not used. This means that the hydrogen molecules are the limiting reactant because they run out first. So the limiting reactant is the reactant that runs out first and thereby limiting the amount of product that can be formed. The limiting reactant for this equation is hydrogen gas. We determine which reactant is limiting by looking at the number of moles of the reactants and then looking at their stoichiometric ratios or the coefficients in front of the reactants in the balanced chemical equation. The limiting reactant determines the amount of products that we can form in any chemical reaction. Methane and water will react to form products according to the equation below. Here methane and water produce hydrogen and carbon monoxide. Let's have a look at this pictorially. Methane is represented with the black ball for carbon and the 4 attached hydrogen atoms light blue. The water molecules have the red oxygen and then the hydrogen molecules attached here and here. Now let's have a very quick look back to the balanced chemical equation. 1 molecule of methane reacts with 1 molecule of water to produce 3 molecules of hydrogen gas and 1 of carbon monoxide. Okay, so 1 molecule of methane and 1 molecule of water produce 1 molecule of carbon monoxide and 3 molecules of hydrogen gas. These two react, and these two react. What you can see is that we have 2 molecules of water that are in excess in this chemical equation. The limiting reagent then is methane. So the amount of methane that we begin with will determine the amount of products that we can form in this particular chemical reaction. The water molecules are used up first, leaving 2 methane molecules unreacted. So the amount of products that can form is limited by the water. Water is the limiting reactant, and methane's in excess. So what are the steps for solving stoichiometric problems when a limiting reagent is involved? First of all, we write and balance the equation for the reaction. Then we convert known masses of reactants to moles. Using the number of moles of reactants and the appropriate mole ratios, we can determine which reactant is limiting. Using the amount of the limiting reactant and the appropriate mole ratios, we can work out the number of moles of the desired product. We can then convert the number of moles of product to grams of product. So you know that a chemical A reacts with chemical B. You react 10 grams of A with 10 grams of B. What information do you need to know in order to determine the mass of product that will be produced? To determine the mass of product that will be produced when we react 10 grams of A with 10 grams of B, we need to know the mole ratio and also the product they form. In other words, we need to know the balanced chemical equation. Let's assume that they react according to the following equation. 1 mole of A reacts with 3 moles of B to give 2 moles of C. We need to convert the known masses of reactants to moles. And then we need to determine which reactant is limiting. We determine that B is the limiting reactant. We can then compute the number of moles of C produced based on the number of moles of B reacted. Looking at the ratio, 2 moles of carbon per 3 moles of B. So 0.333 moles of C is produced. Now we can convert the moles of C to grams of C using the molar mass. 8.33 grams of C. We must always think about how much product can be formed by using what we're given and the ratio in the balanced equation. Which of the following reaction mixtures could produce the greatest amount of product? Each involves the reaction symbolised by the equation where hydrogen gas reacts with oxygen gas to give water. Would 2 moles of hydrogen and 2 moles of oxygen produce the greatest amount of product? Or 2 moles of hydrogen and 3 moles of oxygen? Perhaps 2 moles of hydrogen and 1 mole of oxygen, or 3 moles of hydrogen and 1 mole of oxygen? Or option E, each of these, A to D, produce the same amount of product. All of them are correct because you have to look at the stoichiometric ratio of the reactants. So now let's consider the equation 1 mole of A reacts with 3 moles of B to give 4 moles of C. If 3 moles of A is reacted with 6 moles of B, which of the following is true after the reaction is complete? A is leftover reactant because you only need 2 moles of A and have 3. A is a leftover reactant because for every 1 mole of A, 4 moles of C are produced. Or is it B is the leftover reactant because you have more moles of B than A? B is the leftover reactant because 3 moles of B react with every mole of A. Have a look at the coefficients in front of A and B, and have a look at the ratio that the two reactants are being reacted in, 3 moles to 6 moles. A is the leftover reactant. How many grams of ammonia can be produced from a mixture of 3 grams of nitrogen gas and hydrogen gas? Well, first of all, you've got to look at the ratio that nitrogen and hydrogen gas react in. If you've got 3 grams of each, you need to determine the number of moles that you have of each and compare them to the molar ratio. Then you need to determine which one is the limiting reactant and use that limiting reactant and the molar ratio between it and the product to determine the moles of product formed. Once you have the moles of product formed, of course you can use the equation to convert to grams. The correct answer is 3.65 grams. Now, as I mentioned at the start of this lecture, the percentage yield is an important indicator of the efficiency of a particular laboratory or industrial reaction. According to an examination of a balanced chemical equation, we can predict the amount of product that should form given a certain number of moles of starting limiting reactant. However, our predicted yield of a product is not always seen. Chemical reactions don't often go to completion, and sometimes there are side reactions that use up our reactants or products. So the percentage yield is a useful measure of how efficient a particular reaction is at forming the products. So we have a term called the theoretical yield, and that's the maximum amount of a given product that can be formed when the limiting reactant is completely consumed, according to the stoichiometric ratio. The actual yield is the amount that is produced in a chemical reaction. It's usually less than the maximum expected. The percentage yield is a ratio of the two terms. We put the actual yield of a reaction over the theoretical yield and multiply by 100%. So remember that we reacted A and B to give C in the ratios shown in the balanced chemical equation. We determined that 8.33 grams of C would be produced. When you look at the reaction in the laboratory, we actually see that only 7.23 grams of C is produced. So we can determine the percentage yield for this reaction. We simply put the actual yield over the theoretical yield and multiply by 100%. So this particular reaction process is 86.8% yield. Now we need to find the percentage yield of the product if 1.5 grams of sulfur trioxide is produced from 1 gram of oxygen. The sulfur is in excess. So the limiting reactant is the oxygen. We find out the number of moles of sulfur trioxide produced and use the ratio between sulfur trioxide and the limiting reactant oxygen to determine the number of moles of oxygen reacted. 1 gram of oxygen is reacted. This corresponds to a certain number of moles. If you put the theoretical actual yield, which is 1.50 grams of sulfur trioxide, over the theoretical yield of sulfur trioxide based on the 1 gram of oxygen starting material, multiplied by 100%, you should come up with 89.8%. Let's take a look at this reaction. What mass of P4 is needed to produce 85 grams of PF3 if the reaction has a 64.9% yield? You'll have to work backwards here and work out what we have. We have the percentage yield. We have an actual yield of 85 grams. So you can work out the theoretical yield. Once we know the theoretical yield, we can convert that to moles. We can then work out how many moles of P4 we need to begin with and convert that to a mass. Quite a few steps involved in this particular equation, this particular problem. And there's the answer.